Okay, next we're moving on to kinetics, or reaction rates is kind of a better word for it. Reaction rates. When we do a reaction, we talk about in thermodynamics when we covered it. Thermodynamics tells you if a reaction will or will not occur in nature. It does not tell you how fast it will occur or how long it will take for it to occur. For example, there could be a reaction that has an extremely negative delta G, which, if you remember from thermodynamics, means it's extremely favorable and will happen spontaneously, which means it will naturally happen with no outside help. However, I said a process with a negative delta G that is extremely negative may happen, but you will never see it happen because it will take hundreds of years for it to fully occur, right? For the reaction to fully happen. It will occur, just it will take very long. That's a very extreme example, but it's just something I wanted to note. What determines how fast something will happen has nothing to do with, or very little to do with, thermodynamics, and a lot to do with kinetics, right? The kinetics of a reaction, or the rate of a reaction. So the way we determine rate of a reaction is mainly through this equation right here that's on screen. Rate equals a rate constant, which is, I know it's a little bit confusing, it's also K, but it's different from KQ. That's uppercase K, this is lowercase k. I will tell you how they actually do play together later on, and you actually might have already seen it in one of the previous slides, but yeah, this is lowercase k, which is fairly different from that K, in that rate constant is, firstly, rate constant, I believe, so rate constant does have units. Won't get into what those units are, because those units are not actually the same every time. Depending on the reaction, the units actually of K, of rate constant K, actually change, right? So it actually doesn't have one set of units, it has different units. Whereas KEQ is unitless, it doesn't have units. That's why you can do something like partial pressure over partial pressure, or concentration over concentration, because it doesn't have units, right? So it doesn't matter if you're using pressures, concentration, doesn't matter what you're using, mole fractions, whatever. It's unitless. So as long as you have the same units on top as you do on the bottom, it's all good. Okay, but we have this little k. Then we have concentration of A, which is some reactant. Then we have concentration of B, which is some other reactant. And then you could have a C, D, E, F, whatever, how many reactants you have, right? And these are just concentrations like you've seen, and hard brackets always means concentrations. The tricky part is this lowercase a, this lowercase b, these exponents. Like I mentioned in equilibrium, exponents reflected coefficients. In reaction order and reaction rate, they do not reflect coefficients. For example, something like our example that we've talked about all day, N2O4 to NO2. When you're looking at the rate with respect to NO2, lowercase a, the exponent would not have to be 2. It could be 2, but it doesn't have to be 2, right? It could be 1, it could be 0, it could be 2, it could be 3, right? We don't know. The only way to really know is if they either tell us, or and how scientists actually find out is through experimental means. So the orders have no correlation to stoichiometric coefficients. The order of each reactant can only be given to you, since you're not doing experiments. Obviously, you can't find it experimentally. Each reactant can be 0th order, 1st order, or 2nd order. There is also 3rd order. This won't really come up in the MCAT, at least for a single coefficient, right? For example, if A has an exponent of 1, it's to the 1st order because it has an exponent of 1. If B has an exponent of 2, it is to the 2nd order. But B is to the 2nd order and A is to the 1st order. The order of the reaction with respect to A is to the 1st order. The order of the reaction with respect to B is the 2nd order. the order of the reaction overall is the sum of all of the orders of each reactant. So if you were finding the order of the reaction as a whole, it would be 1 plus 2, because it's with respect to A and with respect to B. So it's 1 plus 2, it would be a third order reaction overall. But with respect to A, it's a first order. With respect to B, it's a second order. Okay. Okay. So another quick poll question. Okay. All right, manning the poll. So the most popular answer by a majority was C. However, the answer is actually D. And this is kind of what I expected, because this is a trick question, actually, right? But it's a trick question they may ask you on the MCAT, right? This is very similar to an MCAT question. They do sometimes actually like to give you trick questions on MCAT. So don't think this is above them, right? So the reason that you can't determine this is because it mentions second order reaction, right? Concentration of a reactant in a second order reaction is increased by a factor of 4. What I'm assuming, and the reason why many of you picked C, is because you assumed, well, if the concentration was X squared, multiplying it by 4, turning it to 4X would mean 16X squared, right? And that would be true, right? That would be exactly true if it mentioned that the reaction was second order with respect to the reactant, right? If it said that A had order of 2 in this reaction, what it actually said was that the sum of all of the reactants, so A, B, C, whatever, the sum of all of these is 2. We don't know if A is 2 and B is 0 and C is 0. We don't know if A is instead 1, B is 1, C is 0. We don't know if A is 0 and B is 2 or something like that. We don't know, right? Because they didn't mention what the order was with respect to the reactant that we're looking at specifically. If it was, for example, if it was to the first order with respect to the reactant we're looking at, and there was another reactant that was first order, we would have a second order overall reaction. So this statement would still be true in the question, but by increasing it by a factor of 4, it's not C, it would be B, right? It would increase by a factor of 4 because it would only have an exponent of 1. If instead it was a 0th order with respect to the reactant we're looking at and second order to some other reactant, increasing it by a factor of 4 would give A as a correct answer and not B or C, because anything to the 0th power is 1. Doesn't matter if it's 1, 10, 50, 100, right? Increasing it would have no effect. That's why we don't know. It could be A, it could be B, it could be C. We can't determine that. Next, we're going to talk about rate determining step. Rate determining step is what happens when there's a reaction that has multiple steps, right? So we may write A plus B plus C equals ABC, right? This may be how we write a reaction overall. However, most reactions don't happen in one step, especially complex ones. Like the one I showed you earlier of the glucose plus O2 going into CO2 plus H2O. It looked so simple because it looked like it was in one step, like it just happens, right? That actually takes like many, many, many steps, and you'll actually learn about those steps when we cover biology, right, and biochemistry. So something like that looks simple, like A plus B plus C goes into ABC, is not actually how like that, right? When you expand it, it's actually multiple different steps. So for example, like this, A plus B goes into AB, and then AB plus C equals ABC. What does this have to do with kinetics? Well, each of these steps doesn't happen at the same speed. And if you see, some of these steps may be slow, some of these steps may be fast. And when they say something is slow and fast, what they mean is there's a big difference. It's not like slow takes 5 minutes and fast takes 3 minutes. It's more like slow could take hours, whereas fast could take milliseconds, right? Something like very extreme differences. When we determine the rate of any reaction overall, so for example, if we were determining the reaction of this whole two-step process, A plus B plus C equals ABC, we would basically be ignoring any fast steps like this. We would be ignoring this, and we would just be focusing on finding the rate of this slow step, right? Why that is because the slow step is essentially 99.9% of the whole rate, right? I kind of like, and I've said this before, it's kind of like if you're cooking, for example, if you're cooking like, if you're like slow roasting some kind of meat or something, and it takes 8 hours to cook, and but before you start cooking for 8 hours, you have to chop up some vegetables, and it takes 2 minutes to chop up vegetables. When somebody asks you, how long does it take to cook this meat, right? You would say 8 hours. You wouldn't say 8 hours and 2 minutes, right? Because 8 hours is such a big time compared to 2 minutes that it's actually not worth mentioning the 2 minutes, right? It doesn't make a difference, right? It could be essentially just a rounding error. And the same thing applies here. The slow step is so much slower than the fast step. Then when we're talking about the reaction, the whole thing overall, we don't really care about how long the fast step takes because it basically took no time compared to the slow step. And that's why we call the slow step the rate determining step, because its rate determines the rate of the whole reaction. It's the rate determining step. So therefore, the rate of multi-step reaction, we always set it equal to the rate of the slowest step. In this case, step 1 is the slowest step. And so the rate of the whole reaction would be rate equals K1 times A to the power of X times B to the power of X, right? Which, if you look at it, is just the rate law that we talked about earlier applied to this thing, right? If you looked at, if you applied the rate law to overall reaction, it would be different. It would have C in there as well, but we can't do that because that's not a step, right? It's a process. This blue part is a process, it's not a step. We can't do that. And we could apply the rate law to this step, but like I mentioned, the rate is so small, it doesn't matter. If instead the second step was a slow one, the equation would instead be, actually did this incorrectly. I should say K2 AB. Now again, I'll fix that when posting. The rate would be K2 concentration of AB to the X, like that, okay? So let's talk about intermediates, right? And this is actually similar to the reaction we've been looking at all day, right? If step 2 is the slow step, the equation would have the rate law of, again, I made this mistake here as well. It should be K2, not K-1. So it would be rate equals K2, concentration of N2O2 plus times concentration of O2. However, we don't know the concentration of N2O2 because concentration of N2O2 is intermediate, right? An intermediate is anything that doesn't appear at the beginning of the reaction or at the end of the reaction. So for example, if you look at the reaction overall, N2O2 doesn't appear at the start or at the finish. It only appears in the middle, right? It's just something that appears in the middle and then just disappears before the end, right? Intermediates we don't include in rate laws ever, right? Because they're just too hard to measure and too hard to use essentially effectively. But the rate law calls for us to use the concentration of N2O2. Well, the way we do that is we actually have to do just a bit of math, right, to solve it. We know that the concentration, that K1 times the concentration of NO squared is equal to K-1 concentration of N2O2, right? Since it's in equilibrium, right? And that's because we talk about an equilibrium, the rate of the forward reaction and the rate of the reverse reaction are equal in an equilibrium. This is an equilibrium. And what fast equilibrium means is that as soon as you put in the NO into the beaker, it'll start up and it'll very, very rapidly just go into an equilibrium, right? It'll set up an equilibrium very fast. It doesn't take very long to get into an equilibrium. So that means the rate of the forward and reverse reactions are equal. We can apply the rate laws and set them equal to each other. We can then solve for concentration of N2O2 using this rate law, right? Because we can just isolate it. We can just isolate it like this and set it equal to all of these values, which we will know, right? We know what the initial concentration of NO is because we're putting it in, so we hopefully know it. We know what the value of K1 is. We would have done that experiment before. We also know what K-1 is. Again, we would have done that experiment before, and we could easily figure it out. So now we can take this overall rate law that we started with, which we couldn't use initially because it had an intermediate in it, this N2O2. We can't use intermediates. But now that we solved for what our intermediate equals, we can now substitute this whole thing into this equation and actually get rid of the N2O2, right? And we can actually get this as our rate law, right? Hopefully that makes sense. So we just wrote the rate law of this step because it's the slow step, just how we would normally write it. And then we just simply, because we couldn't use the concentration of intermediate, we then had to just solve for the concentration of intermediate, which we could do here, right, using this equation. And then once we isolated what it was equal to, we could just substitute in, which is something you very commonly likely have done in physics, math, any type of math-based science. K-1 is not saying that it's the negative of K1. What it's saying is it's the reverse of K1. It's the reverse reaction of the first reaction. So K1 is the rate of reaction 1. K-1 is the rate of the inverse of reaction 1, right? It's the reverse reaction of reverse reaction 1, essentially. It's the backward step, if you want to think of it that way. It's the rate of the backward step. Next, we want to talk about activation energy and curves, right? So first, I want to just annotate this. So like it says here, the x-axis represents the reaction progress from start to finish. The y-axis represents Gibbs free energy, which is delta G. If you guys remember from the thermodynamics lecture we did, right? Delta G, right? A system always wants to have as low Gibbs free energy as possible. Likely, most of this, at least up until like this point, all of this is actually like a negative value. So like 0 would probably be somewhere here, maybe even higher, right? Everything might be negative, right? And the more negative delta G value is, the more favorable it is, right? So we want to have a more negative G value. And even in a positive G value, we really don't want to have a high positive delta G value. We want to have as low a G value as possible. So the system always wants to have as low Gibbs free energy as possible, and so we'll move towards a state that has less energy spontaneously or without outside interference, like we mentioned in our thermodynamics lecture, right? And you've probably seen this kind of curve, right? Starts off at a certain energy value, goes through bumps, and then it ends at a lower energy value. It goes from high energy to low energy. But in order to go from high energy to low energy, it needs to overcome this bump and then again this bump, right? And that happens as a reaction proceeds, right? And a reaction won't really start unless it overcomes this bump, right? And you can see that it takes a lot of energy to overcome that bump, right? It's a huge rise in energy costs, right? It's very difficult for something to do on its own. It has to be essentially jump started. Something to like a car needs to be jump started in order for the reaction to proceed. This is called, this value that is required to jump start it is essentially called the activation energy, or EA. And it's written here. And it's the value from this starting energy to the top of this hill, right? And this is the hill it needs to overcome. And again, this is a multi-step, this is the curve for a multi-step reaction, right? This is reaction 1, and this would be reaction 2, and this would be the product. So this would be the intermediate step, right? And then from the intermediate, notice the intermediates are a little bit higher energy than the reactants, but it gets the intermediates, and then it's a little bit of another hill, another activation energy, and then you go to very low energy products. Okay. But like I mentioned, it could take months, years for a reaction that on paper has a negative delta G value, right? Look, it starts at high energy and then it ends in low energy, right? So this would very easily happen. Well, no, it won't, because sometimes this mountain is really high and it's very, very difficult. It takes months and months and years for it to randomly get a spark, if you want to think of it that way, to jumpstart itself. However, there are these things called catalysts. A catalyst is a compound that appears at the beginning of a reaction and at the end of a reaction completely unchanged. This is kind of the opposite of an intermediate, which appears only in the middle, doesn't appear at the start or the end. Catalysts appear at the start and the end unchanged. They also appear in the middle. However, they may be changed in the middle, right? And most actually are. That's how they work, right? They have some kind of favorable interaction with one of the reactants, or more commonly with actually the intermediate, right? Because if you noticed, the intermediate, so reaction 1 is actually kind of hard to do because it starts off as a low energy and ends up in a higher energy position than it started with, which is not very favorable. What a catalyst can do is kind of alleviate this by having special interactions with the intermediate. But the way this looks like on the graph is actually, and I'll show you in a second, actually looks like this, where it lowers the activation energy. It fulfills a very important function by increasing the rate of reaction. So if a reaction is thermodynamically favorable, but may take hours or days to happen on its own naturally, with a catalyst, it can speed it up so it takes seconds to happen, right? It can have a massive, massive influence, depending on how good of a catalyst it is. And it allows reactions to occur much quicker. The way it does it, like I mentioned, is by lowering activation energy required, right? So if you want to look at it here, this is the reactants products you notice from high energy to low energy. But without a catalyst, it has a very high hill that it has to overcome, right? It needs a big spark to get it started, jump start. But if you add in a catalyst into the reaction, it greatly lowers the activation energy required. And now this is a much easier hill to overcome, and it's much faster to overcome it. Notice how a catalyst doesn't change the starting energy. It's still the same no matter whether you use a catalyst or not. Starting energy is the same. The final energy is the same. The amount of energy at the beginning or the end doesn't change. The only thing that changes is the activation energy. That's the only thing a catalyst can do. Okay. Reminder that all enzymes are catalysts. An enzyme just means that it's a catalyst that shows up in our body. It's a biological catalyst. So all enzymes do this, right? All enzymes have this as their primary function, which is to speed up biological reactions. If it wasn't for enzymes, biological reactions, all of the reactions in our body would have this kind of energy, and they would take much, much, much longer for them to occur. And we would probably die because we would have no energy, and it would take way too long to make energy, and we couldn't survive, right? So enzymes are very important. Catalysts are very important in industrial chemistry. Okay. So last clicker question of the day. I believe we only have a couple more slides after this, so we're almost done. So please just take a minute or so. Okay. Turn on the phone. All right. So actually, everyone picked choice B, which I'm happy about, and I guess I kind of nailed the point. Nailed home the point enough. Catalysts increase the rate of reaction by lowering activation energy. Again, A is not correct because they are not used up. They have to be present at the end of the reaction completely unchanged in order to be considered a catalyst. Otherwise, it's just another reactant. Catalysts alter thermodynamics. No, they don't. They don't change the delta G at all. All they affect is the kinetics. Okay. Catalyze, stabilize the transition state by bringing it to a higher energy. Again, doesn't change the energy, just change the activation energy rather than the energy of the transition state or the products or reactants. And also bringing it to a higher energy would actually make it more unfavorable. Okay, so that was the last lecture, but there was another slide that I wanted to cover, right? We talked about little k and big K, right? Well, there was this slide, which I'm not sure if any of you guys noticed, but KEQ equals KF over KR. And notice how this is lowercase k, and F means, in this case, forward, R means reverse, right? I wrote it as K1 and K -1, and oftentimes you'll see K1, K -1. This one uses KF, KR, doesn't matter, means the same thing. The equilibrium constant is also proportional to the rate laws, right? So the higher the rate laws, the higher the equilibrium constant. What that means is, for example, if the forward reaction happens very fast, that means, and compared to the reverse reaction, if the forward reaction happens very fast compared to the reverse reaction, at the end, when it does eventually reach equilibrium, the KQ will favor the right side and more of the product will be created, right? It'll favor the forward reaction. Very simple, but I just wanted to show that these two K values are related. And here's this slide. Again, in equilibrium, there are two reactions with two different K values, but the rates should be equal at equilibrium. Again, forward reaction, reverse reaction, K1, K -1. The equations are also different. The forward reaction has this, while the reverse reaction has this. But again, you could set them equal to each other and essentially say K1 N2O4 equals K -1 NO2. Okay. All right. So that's it for today.